Great. So thanks for having me. So it says pre-training models is an LLM VLM talk, and I think it's a fun talk. I'm not sure if there are too many insights in this, so let's go over the material. Okay. I think that. Do you like LLMs? What is the general position here? Do we like LLMs? Do we hate LLMs? We are indifferent to LLMs.
Somewhere in the middle, I guess.
Some, which I have three. And I said, okay, so Yorgos is indifferent to LLMs. So here's my position to LLMs. I think they have matured enough that how do I put it that? So they are, I think, too good not to be used and not good enough to be used. So we need to figure out what to do with that. And we may decide that we don't want to do anything with them, but even that should be an informed decision. So I think that they can be good interfaces between users or designers and machines that we built, and the type of problems that we have. I'm looking into it, a couple of fold here, how they encode some knowledge, how to leverage that additional knowledge as for building autonomous systems or robots, etc. The second is if we use it and if the system operates, how can we talk about verifying the generated behavior, whether it's going to satisfy requirements or not. And then, of course, the very nice outcome of verification is usually not that it is verified, but it is not verified. And with that comes a little bit of an insight whether we can use it to refine the prompts. But in the second half of the talk, I'm gonna try to use these outcomes to actually refine the models themselves. And then another very useful thing, at least from where I stand, I said this earlier to someone, I've been working on problems that relate to autonomous systems for a while, and any autonomous system will have to understand the world around them in some way, perception. And I had no idea how I can approach perception, but now the visual language models give a neat way of, they are lowering the bar for people like me to also think about perception more directly. What is going on? Okay, so that is those are the motivation. Today I have 3 pieces of work, and to make it more confusing, I list them as 4 things. The first 2 are related to each other, and then and they are essentially extracting controllers from interactions with language models, and then thinking about their verifiability. And then the third piece is using verification to fine-tune LLMs, and the other one is a little bit different. I will come to that, and we'll see what it is. So let's get into it. In all this work, automata, finite state representations act as a glue. So on one hand, we have a way to interact with these models that use natural languages there as their interface, and we want to build algorithms on that. And I think automata is just the bridge between them. And of course, we can develop tons of different algorithms for different purposes that work on automata. And when I say automata, I actually use it loosely, just finite state representations of things. Okay, so that's going to act as a glue. And I had this slide at the beginning, partly because whenever I gave this talk early on, I was asked, hey, such and such is looking into extracting specifications, let's say temporal logic specifications from language models. Why are you not doing it? My answer to it is I don't. I prefer to work with automata, but also I feel like if you work on extracting specifications from language models, please do not get offended. But I think that's we don't need it anymore. Why did we ever want to work with formal languages? It is sort of understandable, but more importantly, we can actually develop algorithms on that. We can do math on that, right? But I can develop algorithms based on automata. What is the shortcoming of automata? It is probably not that understandable by humans. But now with language models, we have a natural interface to natural language. What is more understandable for humans than natural language? And then we can, if we can tie it with automata, then I can also develop algorithms based on that. So it looks to me that in this context, extracting formal specifications from language models, I think it is debatable whether it has value or not. So we will work with automata as intermediate representation of things. Everybody knows what model checking means? Raise your hand if you don't. Don't be shy. If you don't, raise your hand. Okay, you know then, right? Just I can assume that. Even if you did not, this is the only slide I have on model checking. So you pass a model, compose with whatever you want. So you pass a model and then ask whether specifications are satisfied or not. And it is yes or no. If no, then there's a counterexample. That's it. So one of the very early pieces of work that we did, this really goes back to when GPT was becoming just coming out, and we wondered, hey, this thing is coming out, or this seems to be doing something. What can we do with that? And the starting point here is really the input to the process is cross the road. So at some high level, the user specifies what they want to do, and the purpose here is extract a controller that we can then try to verify. And so it starts with that. Then it just if you pass this to a language model, and you can probably also specify the format of the output, but you can get something like this relatively easily. So it gives you steps for crossing the road. There are 3 steps to it, and then if you want, it can give you sub steps, etc. Then you can parse that output, and from that parsing, you can start getting what might be a useful proposition to pay attention to, what might be the relevant actions, etc. And then that you can just map it to essentially a finite state representation. That's all there is here. And okay, let's go through the slide. And then for this cross the roads, if that's the outcome, with that parsing to a template, you can actually get out of these autonomous propositions, as I said, what the output symbols are. And then out of that, you can build these things. There's nothing really, there's nothing much here, but I think even this, I don't care about the automaton that much or the finite state model that much, but there might be applications where figuring out what autonomous propositions to use to represent the world. If you can automate that process, that by itself is not that useless. And the evidence is that interactions with language models may help with that. Yeah, so let's proceed a little bit. Then, of course, you can start asking, okay, you have these steps, but can you elaborate on the steps? You can get sub steps, and you can build, you can expand your automaton. One thing that we realized was, of course, and this is not a surprise at all, the automaton that we got, even for this very simple case, can introduce, how do I put it, inconsistent or not natural steps into the automaton. And just you cannot blame a language model for that. It was not built for building simple controllers for crossing the road. What happens there is that it indeed crosses the road, but then somehow it just continues going back and then crossing again, going back and crossing again, etc. So that is one thing that we will try to actually identify and resolve using verification. But anyway, so now we have that finite state representation. And of course, you can start now also throwing in specifications into the mix. You might have independently given specifications, and you might be interested whether this whether the controller that you extract, that middle thing, against a model of the world, and let me try to have a couple of comments on that in a second, satisfies a specification that you care about there. And then, of course, different controllers that you extract or may or may not satisfy, or if you use the same controller against different models of the world, the specifications may or may not satisfy. The point is that you may or may not be able to verify. So if, and in the case that is not verified, can we use it to refine this, what we have? This is what I already discussed. And then now you have the verification question. If success, you must be happy because based on what you know about the world, you have a finite state object that satisfies the specification. So there's not much else you can do. If not, then we may be able to actually refine the controller, and that is essentially a counterexample guided in codes model refinement. So this is going to go into refinement, and this refinement is you change the questions that you ask, or you ask further questions, and you try to refine that representation of the controller that you have on the right-hand side. This is against the same fixed world model M, and you run this verification, and then this doesn't pass. There's the counterexample that it seems like you might get stuck in some state P1, and then you pass that, and the new query is refine the following steps by with an action. Whatever it reads. So you actually try to guide the further queries and refine them. This one now, I don't remember exactly whether it's going to pass or not. No, it did not. There's another counterexample, P0, P1, whatever. And then the third one is going to pass. So and this is essentially trying to localize where things might be going wrong and turning that into a query. Going from those counterexamples to natural language, there's nothing universal about it. You just, somebody needs to look into that and interpret that. Even though I guess, let me just say this work was indeed done maybe when I was visiting you guys several years ago. Things have evolved. I don't think that still they can necessarily close your eyes. They will not be able to build controllers that would pass verification, but things have changed. And if things haven't changed with language models, they have changed us. We start asking these paranoid questions, right? Anyway, let's move on a tiny bit. So that is the extraction piece. So you have a controller. Now, let's say you verified against some world model. The next piece is really, this. So this robot now, let's say, it's going to take that controller and it's going to implement. And then if you look at it, there are propositions there. It says, let's take that self transition from Q2 to Q2. It says not turn green, right? It needs to read that from the world. Who's going to give that to the robot? So when my earlier comments about that lowers the bar for perception, it is exactly that. In my previous life, actually in this current life, but earlier, I would have not cared about it, but now we have a chance to actually start playing with that, right? And that is essentially the visual language elements come in, and these images are a student went out with an iPad and took these images, and then you process it using a visual language model, and then just take a couple of thoughts out of that. So how is this going to work? Again, there are these propositions. Now you will pass something about them to a pre-trained multimodal model, vision and text processed together, along with the images, and then it is going to tell you whether about something about the truth values of those propositions, and then you can take that and implement that. And of course, so if you take it, and from starting from there, a traffic light, yes or no, and from there it is going to go on at every step. You will consult a visual language model. By the way, I'm not saying that for these simple things you should use visual language models. These things are expensive, right? But the cost is coming down, and actually some of these things can be implemented on even some small robots now. Anyway, just go on like that, but you will also make mistakes, right? Just the outcomes of these things. If you play with a vision language model or any perception algorithm, if it says it is a green light, there's a good chance that it is not a green, right? So one question is what to do with about that. So shall we worry about those uncertainties or not? We decided to think about it at least. And if you look at that, with some decent likelihood, this left image actually is predicting that light is green and the light is not green. So if you are trying to run a robot there or whatever, then that could be a problem. You look at this and it says green and it is red and you jump on the road. So whatever that scale is, so one like trivial way of trying to deal with this, if these numbers are sufficiently high or low, then you will act on them, and if not, then you call it uncertain. And what would you do in that case? You're at that light, you fall in that the number is not sufficiently high or sufficiently low, whatever sufficient means. Let's put it aside. What would you do? You would tilt your head and look, right? Maybe you will see if it is like the lighting conditions that was making it hard. A tiny bit of changes might do it.
And you could look at other lights on the crosswalk.
Oh, that could be very sophisticated. Totally.
Yeah.
Actually, just a group of students very recently submitted something like that using multi-agents and VLMs, and then what is the information that needs to be exchanged, etc. I just didn't have slides on that, so we will talk about the simpler version. So that was the first thing that came to mind. Like take a little bit of yes, physically do not move, but not every action has to be. After all, just staying still is also an action, right? You can try to change things, and merely actually taking one more image from the same angle might be sufficient, because if you push the same thing, even with the slightest tilts, and that might make a difference. Even the same image may, I don't know how it would affect about that. Anyway, so this not that we did that, but this I think motivates how to more actively use these things. If you find yourself not being able to resolve the uncertainty, you might try to resolve that with these different angles, or actively deciding how to look into things. So what happens here is that we just you append the underlying automaton with these additional uncertainty flags, and then if you cannot resolve the uncertainty, you just stand still or stay there and try to gather more information. One thing that, again, this doesn't include is this only flags things as uncertain, and you stand still. Of course, you need to do something around that at that time. This only has that, again, with uncertainty, you stand still. What you do during that, you could be much more clever than what we have. You can try to encode what would be the actions for changing your angle, etc., and get into more active perception coupled with this decision making. We haven't done that in this work, but I think that is very meaningful direction. Okay, so what happens here is this is false, you take that action. This is uncertain, you stay there, and you take one more image, and now the numbers are above or below the threshold, whatever it is. You have more confidence and you proceed. So that is how we thought this could more directly relate to perception of the world, etc. So putting these things together, again, so the top level is was interacting only with an LLM and only for building these controllers. And then once verified, then you implement that. And the bottom part is the interaction with this pre-trained multimodal model, and then it would run during the execution. So that is that. So and this is I'm going to proceed. I'm going to now ask a different question. So this is and then this automaton extraction, etc., has become a workhorse for a good number of other problems that we looked into. And I'm going to now just discuss a second problem. This is how verification outcomes might help us fine-tune language models. This is getting a little bit closer to current day. This is still a line of work that we continue in different forms. What do you know about fine-tuning language models? How is it done? If you're a language model, you can just process this for me. What? Humans, for instance. Humans, right? It's what your humans do.
Like it or didn't like it.
Did they like it or not like it? Yes, exactly. Yeah. The first performance boost OpenAI reported was they had this image, and what happens is just you run on your existing historical labeled or whatever data for forever, and at some point you stop and you start asking humans if you like it or not. We still indirectly do it, probably, but you realize that OpenAI has actually this thumbs up or thumbs down thing, right? I never click it, but initially it wasn't like that. I think initially actually OpenAI went to some country where the labor is much cheaper and deployed tons of people to get that initial boost and the flashlight. So how can we, the question that we asked was, since we had that initial thing that we extract automaton and try to verify, etc., the question that we asked was, how can we use that trivial functionality to fine-tune language models? So I'll go into that, but let me just actually set the expectations properly. When I talk about fine-tuning, the purpose here is not creating a better LLM that you can put on OpenAI website and would compete with an existing LLM for all the purposes that it has. The point here is, in a context in which we want to use an LLM, can we fine-tune that to do better than general purpose LLMs within that context? And that context is a context in which verification matters, and we can run verification. And one of the early reasons that I tried to sell this thing to my student was, let's say Tesla trains a big model, and it is going to be data from all over the place. Now they go to a new city, they want to try to autonomously drive. Actually, Tesla is so outdated and so conservative, far right now in the US. Let's use a different example, Waymo, as if they are different. Waymo does this, okay? This is recorded?
Yes.
We love Tesla. We love Tesla. But let's use Waymo. So they have this general purpose model, but they go to a new town now. It's a different group of people, different even conventions, different rules, different layout, etc. The question is now, how can we, let's say, relatively more efficiently use data and outcomes of verification, whatever insight we can generate in that context, and create a model that would be better than the general purpose model in the context where we will use it. Okay, so the context is going to become important. This is not a way to improve LLMs in general. It is within the context in which we can run verification. And the point here was they remove the human feedback and put formal methods feedback there. So here's how it's going to work. Let's say, again, we have a model of the world. It can be a simulator, an abstract model, etc. And then the user comes and have some specifications. And there is some flow, blah, blah. You go to a language model. And as we did before, instead of creating one response, we'll create multiple responses and map them to a controller, which I think the next slide is about. But from that, automated feedback is going to be generated, and the feedback is going to be essentially the ranking of these responses. And once you rank these responses, then there are existing algorithms that also were used in fine-tuning language models. I think there are libraries to implement them, but that ranking information is used as the feedback to fine-tune for fine-tuning purposes. And what has been automated here, what is automated is the generation of that ranking, which is essentially what humans like or not is doing. So with that, so yeah, the fine-tuning goes and works. And then here's a little bit of a like a zoom into that one box there. You generate two responses, you turn them into finite state controllers. You have a set of specifications that you care about, you check against them. And then let's say response one satisfies three of these specifications, response two satisfies only one of them. Which one would you like? Right, response one. And then that is ranking information. Okay, so that is that. Does this work? And I think this is actually like navigating in a city-like environment. If you are familiar with Carla simulator for autonomous driving, just think of a setting like that, because I'm going to come to that anyway. So what happens is the controls that you extract out of interaction with LLM, as in the first part of the talk, it is hit or miss. Some of the specifications are satisfied. In this case, I think there are 15 or so specifications in the list. Early on, the trend here is that as you fine-tune, the number of specifications that are satisfied by the controls that are extracted is increasing. So then we can also do these things in cases in which the world model is of course, pretty much anything that's in general a higher fidelity simulation. And in this case, of course, you cannot do the exhaustive verification. You will just do something statistical and try to just rank the outcomes of the language model. And there's a similar improvement before and after the fine-tuning for in these specifications.
So in this thing, the language model creates the controller. It doesn't drive the car. It just creates the controller,
Yeah.
and then it's done. There's no feedback to the language model after that.
There is a feedback, but not for driving the car. In this particular case, you extract controllers, you drive them, whatever, you gather sufficient, you gather data that would be useful for statistical or empirical verification of this thing. That ranking information goes back to the refinement of the language model. Okay, so so this epoch is, each of them is a refinement step. You verify in whatever way you can. Once you have the ranking, you use that to change something in the model, extract, repeat. None of this is, of course, online. This is all design time. So these are coming from two different sets of slides. There's a little bit of repetition between these messages, but I think these several slides have more information in them. I decided that I would use them. So what happens? A couple of specifications, and this one shows, and the setting here is this this robot, and part of the reason that robot is there because students actually took it and put it on the robot. So what we see here is different specifications. And before fine-tuning, if you look at this, whatever this color is, blue or purple, it shows probability of satisfaction. And don't ask me where this probability is coming from, what the underlying probability space is. I don't remember what it is. Okay, it's probably just repeated runs of the same thing and then seeing whether it works. What we see is that before fine-tuning, and this shows the outcome at different fine-tuning stages. The end result is with 350 iterations, and in between 130 and 230 iterations. As you can see, there's some. I don't think it has to be steady, but there's some steady improvement in this data. And I think the more striking thing is consistently it goes from 50%, 60% to about 90%. And I don't know what numbers, these numbers do not mean anything, but just the amount of the trend and the amount of improvement, the relative improvement, I think is pushing the outcomes from coin toss to, yeah, let's start talking. All right, just the this non-negligible improvement, and these are not actually. First of all, there's no labor in this, but they also don't run like days or weeks as like or on huge machines. These are relatively doable things on meaningful laptops. So then I think this figure is also I like talking about this figure. So what we see here is the outcome that we have from so here's what's going to happen. So the blue one is in today's standards, it's a small model. It is a 7 or 8 billion parameter model. And then red is another small model. And the others are the next two, this whatever this whitish color and the grayish color are, they are large models. And you extract these controls and try to verify, and then the product of satisfaction. And what we see is, of course, the large models, and these are 200 billion type parameter type models. Of course, they perform better than the small models. But what we see is that you can take the small model and fine-tune them and exceed the satisfaction probabilities. So if this is within the context, then even small models can do better than large models. And why 8 billion parameter model is a small? Because that is the smallest that we can easily find these days. I would love to be able to look into these things, how much it can be actually pushed down. Maybe there's even like I don't know, 800 million parameter model that can do as well as 200 billion model. And why does this make this matter? If we can make these language models small enough, we can just then put them on robots directly instead of trying to, I don't know, you may put them on robots and then we'll figure out what the hell we do. That's, let me just do that. But I think that being able to generate small models as performant as other large models, especially if you can push it toward visual language elements and you use them for perception, that could be meaningful, especially given the sort of the field of generalization these models might have from context to context, or not context, but just use cases to use cases. So that is another result, and so this figure, this slide is about, I believe, this the improvement that we see there is, or let me just put it this way: this is a fine-tuned model that is being used on these two robots, but the fine-tuning was done with the data, not using this robot, a different robot, and not in these environments. And then similar benefits. Probably there's a little bit of a degradation in the improvement that we have from using like a plain model versus a fine-tuned model. But the trend seems to be transferable, at least from similar looking robots to other robots and in environments or tasks that are different from the original environment in which it was used. And there's no claim here that this is always going to be the case. There's no claim here about anything that they will always be the case. As you can see, these are really empirical things. And this would, of course, break. If you fine-tune the model with a robot in some environment, and if you try to do real-time trading with that in Wall Street, of course, it's not going to work. Or if you try to generate better language or something, that is not the claim. But seems like the the fine tuning, the benefits that you get from fine tuning are not necessarily entirely brittle. Okay, so that is the sort of out of domain generalization claim. Not generalization, but just you have an instance where it seems to work out of domain. Yep. There's always a way to do it. I cannot wrap my head around a verification argument in that case. One thing that students look into is trying to do similar counterexample guided refinements, but not the model, instead the prompts that you. And there's a way to do that as an optimization problem, and that seems to buy some as well, improve the performance. Okay. So yes, please.
How do you ensure that what the LLM gives you is syntactically valid for language like that? Are there any data cleaning procedures?
Yeah, no, it's the very first part, we had templates, etc., and just we parsed that. Having said that, though, these things have evolved as well. I think that it will be too big of a stretch to try to ask for outputs that are in the language of the input language of a common model. It of course depends on whether there's sufficient data that they have been trained on. And I said I will use automata as the clue here, which I still believe, but students then later looked into how to directly extract executable software out of it. So it is becoming increasingly possible to specify the output format, and I'm not a LLM salesman, but they seem to be doing fine, and in some cases they do not do fine. But I think these things really do not. If you ask me, the more capable they are, it is making the use of verification in the loop somewhere even more meaningful. Because as they become more capable, people will try to use them for more cases. People will get this false confidence that all these things work. And we have examples. I couldn't fit it anywhere. I have this one slide where you ask for an output. They give me just some software that would, for example, get a robot proceeds straight unless there's a human, etc. And it generates software. And if you look at it, yeah, it's going to do what it's supposed to do. But then it is also very much possible that you can easily create corner cases using verification, etc., where it doesn't. So again, more capability to me is never going to remove the need for verification type thinking. It is only going to make it more critical. We will have to evolve with that, and we will ask different questions. But I think instilling this thought process is a meaningful long-term investment.
I agree. What you said. My question was more rooted the improvement in the responses of the LLMs that you show. They don't include syntactic corrections of the.
Oh no, just the results I have are all just the whatever you can call it automated design. Yes, okay. There's no human anywhere in that. Yeah. Having said that, again, at least early pieces had this templates, etc., and parsing wasn't real templates, so there's not really too much of a room for syntactic mistakes, at least in the early work that we had. Okay, so the next piece is I actually this Anyway, so this is, the next piece is the last one, the gray one. This is copy and paste mistake here. Okay, so this one is a different problem. And this one doesn't even have to be an LLM problem. We looked into it because of language models. We are now trying to extend it to data that is beyond language only, like visual language. But I think that's with these models that allow us to interact with machines at higher levels of abstraction, to me at least, motivates what verification should actually even mean. Because I have these world models, simple finite state world models that I verified, etc. But in all generality, that's not going to be the case, right? It's just these things will probably be much beyond the formal verification view of the problem that we have had. So let me just build it up a tiny bit. So this is I don't know how old it is, but it's most like a year or year and a half. So in the time scales of generative AI, this is like a century ago. The OpenAI had this paper looking into what they, I think, called LLM actually generates outcomes that would be aligned with what you had expected, and the approach there was essentially an LLM is interrogating another LLM, and we looked into it when we thought that formal methods might offer its own version of this. I'm not going to read through it. I think both of them have their own advantages and disadvantages. And we set, we asked ourselves whether we can do anything that preserves a couple of things we like from both sides. And I'm gonna show you what we have. If anybody wants to discuss this one, by the way, I would be very happy to discuss because I think it is.
Les points positifs, à mon avis, qu'il faut souligner, c'est un certain qui crée des emplois sur les notamment pour lesquels je parlais.
So that's not a question to me, right?
No, it's just,
I think it's from the PA system because his sound is not connected. I don't know what the. Like it's not, this computer is not.
You know what? Does it bother you?
Yeah.
It doesn't bother me. Let's just move on.
Just running my recording.
Your recording is verified.
your process recording.
Yeah, as I was saying, if anyone now discusses, I would be happy because this way of thinking is not. I am warming up to it. Anyway, so here's the setting though. Let me just tell you what the setting is. We asked ourselves, what if we have some collection of formal specifications against which we can run verification? And in addition to that, let's say we have a ton of other requirements in natural language. What can we do? And what we do is, even before I open it, here's what we do. Let me open it. Essentially, the specifications against which we can run verification is used to generate training data for a classifier that would separate acceptable from not acceptable. And the training is essentially trying to find the latent space or some space in which separation is possible. What features and what combination of them would matter for us to be able to separate good from bad? Okay, that is that. And then once we have it, inference based on that classifier becomes when you have a new input, you classify using that classifier and label it as good or bad. Right? That's the story. This is what I just told you. So yeah, just use the limited set of specifications that you have to generate training data, and at runtime, when a new rule comes in natural language, or a new plan comes, then you use your classifier to label it as safe or not safe, good or not good, etc. And the training stage, again, just at the training stage, you have. I just told you about this. I'm not gonna repeat it. So you try to, if you don't worry about where to map that data that you have, you may be able to separate that red and blue points that you have in that image. The name of the game is what is the latent space in which this may be separable. So you create a projector that can be represented in any way. It seems like this is neural network in this case, but just find that space where there is some separation between the red and blue. So use your training data for that purpose, and when the again new controller, new something comes, then you just map to it. And at inference time, it is just really this passing the new controller, new plan through the projector, and finding, oh, this is on this side, etc. So that's that. So how does this work? On a couple of examples. First of all, so you have this rule: always yield to a pedestrian. At this point, the projector had been trained. So this is not being mapped to a formal specification. You just push it through the projector that you have. I know, so this is the plan. This is the, and it is given as this text in some special format, but it could have an actual literal text. And in our thinking, this would have come from LLM, but this doesn't have to come from LLM. This is the former comment that I have. Of course, the LLM interaction can automate tons of things in training, etc., but that's a separate issue. So, what is this plan? This plan is a point in this space, whatever that thing is. You push it through your projector, and then it turns out that it is on this side of this classifier, and it is labeled as blue, whatever blue was. All right, and that plan, of course, can then be executed in the real life. And this is actually the case where we had this the code that looked okay. It wasn't okay. What it was doing was actually, I don't remember exactly. It was not paying any attention to the pedestrians and crashing into them, or it was doing it once, but then once it paid attention, if it sees another pedestrian, it did not pay attention to the rest of it. And so this one is refined after this process. So the point of is that a plan is, of course, you can take it on a robot, and a plan is just a point in the space that you try to build a classifier on. Some empirical results. I'm not sure what these empirical results are. Okay, I think what is to be reported here is you can train something that seemed useful in that robotics example, and only with 400 training samples, and that training procedure takes 0.15 seconds. So it's just trivial, essentially trivial. That is the only reportable thing. This figure, so this slide is, I think, reporting on a bunch of statistical metrics on the quality of this classifier based on the true, negatives, false positives, etc. And in each of those cases, it is doing relatively better than the OpenAI baseline, and relatively is also a relative thing. In some cases, this improvement may be actually significant. And the rules are given here, so they are not necessarily, at least the natural language part of the rules. And this was done with 2 pieces of formal specifications versus 5 pieces of formal specifications. And when I say pieces, of course, they could be as long as you want. In this case, I cannot tell you what they are, but they were not. They were just like, you can write with a couple of symbols and no nesting, etc. They were just specifications that a human being would sit down and feel comfortable with in temporal logic type language. So this is what I mean by, maybe we can think about verification against requirements for systems that may implement automated ways of generating code or text or planners, etc. this would be probably the entirety of this could be beyond what formal verification does. And one other thing that actually I want to point to is we usually don't have a shortage of requirements or specifications. We often have a shortage of formal written versions of these things. But take any application, you will find tons of guidelines, handbooks, whatever you want to call. Driver's handbook is one example of that. This way of thinking might actually enable us to work with more general view of specifications. There's one more that the student is looking into right now, which is the ability to work perhaps with graphical or visual representations of what is good, what is bad, or what are the requirements. So if you had a robotics example, and if you somehow opened a couple of books, papers, etc., you found some formal specifications. In addition to that, let's say in a furniture assembly case, you have tons of IKEA handbooks which include some text, but also tons of graphical representations of what needs to be done. Can you use them all together and try to ask planning and verification questions out of that? All right, so this is it. These are some pictures, and the point of the talk was LLMs rock, and everybody should just always use LLMs for everything that they do. So this is recorded still, right? Yeah. So for the people who are actually who may listen, no, that's not the point. LLMs have some promise, and I think we don't have the luxury of ignoring that. But then also they're not good enough. Maybe we should keep our engineering hats and try to put some discipline into using these things. And the way that I know how to think about putting discipline into processes is formal verification. So I try to share my comments about that.